We're looking at homework from section 6.4. This is question number 7. As part of a survey, a marketing representative asks a random sample of 27 business owners how much they would be willing to pay for a website for their company. She finds that the sample standard deviation is 3,514. Assume the sample is taken from a normally distributed population. Construct 95% confidence intervals for A, the population variance sigma squared, and B, the population standard deviation sigma. Interpret the results. So, we need the sample standard deviation, and that sample standard deviation is 3514. Then we're going to have to find the chi-square values for a confidence level of 0.95 and a sample of size 27. Drawing a picture could give us a better idea of what it is we have to do. So we'll draw the chi-square distribution. In that chi-square distribution, we've positioned values chi-square L and chi-square R in such a way that the area between them is the level of confidence, and that they have the same area in each tail. So the level of confidence is 0.95, so 0.9500 is in the middle. In our two tails, that leaves 5% of the area, split evenly, would be 2.5%. As a decimal, that's 0.0250. When we use the chi-square distribution table, we're looking for area to the right, unlike in the standard normal table where we look for area to the left. So if we look at our chi-square L value, what's the area to the right of that position? That would include the central area of 0.9500 and the right-hand tail of 0.0250, which gives us a total area to the right of 0.9750. For the chi-square R value, the area to the right of that is just the right-hand tail, which is 0.0250. Those two areas, the area to the right of chi-square L and the area to the right of chi-square R, will always add up to 1. So you can always do a quick check to make sure that they do. We'll keep that diagram as a reference, and then we'll ask ourselves the questions. What's the area to the right of chi-square L? 0.9750. What's the area to the right of chi-square R? 0.0250. And then what are your degrees of freedom? Since our sample was size 27, our degrees of freedom are 26. So now what we're going to do is we're going to turn to the chi-square distribution table. Let's remember the values that we've got going here. The degrees of freedom are 26. Area to the right of chi-square L is 0.9750, and the area to the right of chi-square R is 0.0250. Next thing we want to find is the actual chi-square L value, not the area, but the value on the x-axis. The way we do that is by using this table. We find our degrees of freedom in the column to the left, and then the area to the right of the chi-square L, which is 0.975 across the top, and we find where those two meet. Those meet at a value of 13.844. So that's our chi-square L value. For chi-square R, we do the same thing, but we use the area at the top of 0.025, and that gives us a chi-square R value of 41.923. So now we have the two values that we need. We can now turn to the formula for the variance. We use these values: degrees of freedom, standard deviation, chi-square L, and chi-square R. The confidence interval for the variance is formed as such. n-1 s squared over chi-square R is less than sigma squared, which is less than n-1 s squared over chi-square L. Notice n-1 is your degrees of freedom. The s is your standard deviation, but we're squaring it, so s squared is actually the sample variance. And then in this fraction, the chi-square R is on the left, and the chi-square L is on the right. At first that seems odd, but when you think about it, it makes perfect mathematical sense. Chi-square R is found farther to the right on the x-axis than chi-square L. That means that chi-square R is a larger value. When you put a larger value in the denominator of a fraction, that makes the value of the fraction smaller. So the left-hand fraction here would be smaller than the right-hand fraction, so the inequality can be true. We're going to insert the values that we have in the correct positions in this equation, and we get 26 times 3514 squared over 41.923 is less than sigma squared, which is less than 26 times 3514 squared over 13.844. When we use our calculator to come up with those values, we get 7,658,161.296 is less than sigma squared, which is less than 23,190,775.5. Rounded to the nearest integer, we get 7,658,161 to 23,190,776. So let's go ahead and interpret these results. Remember, when we're finding a confidence interval, the level of confidence is how certain we are that the population value falls within the interval. So we have a 95% level of confidence, so that means that choice C and D are eliminated because those say 5% level of confidence. And we are looking for the statement that says we are between two values, which would be choice A. With 95% confidence, you can say that the population variance is between 7,658,161 and 23,190,776. Let's look at part B, the confidence interval for the population standard deviation. We've done an awful lot of work and we wouldn't want to do that much more work going forward, but luckily we don't have to because of the relationship between the variance and the standard deviation. Remember that the standard deviation is the square root of the variance. So if we take our inequality statement from the variance and we take the square root of each part, we'll get an inequality statement that applies to the standard deviation. So we had this inequality for the variance. We take the square root of all three parts. When we take the square root of the sigma squared in the middle, it's just sigma, our population standard deviation. And we use our calculators to simplify. We get 2767.338305 is less than sigma, which is less than 4815.68017. Rounded to the nearest integer, we have 2767 to 4816. That's our confidence interval for the population standard deviation. We should check our answer before we move on. And we can't check it completely, but we can at least verify that we are in the right place. How do we do that? Well, we look back at what our original standard deviation was. The original standard deviation was 3,514. That value has to be within this interval. If it's not, we've done something wrong. So because 3,514 is between 2767 and 4816, we feel good about it. If it was outside of the interval, we know we made a mistake and we would have to go back and find our error. So here we're going to move on to the interpretation. We're 95% confident that the population value falls within this interval. So that eliminates choices A and B because those say 5% confident. And the only one of the other remaining answers, C and D, that has a value between two values is choice D. With 95% confidence, you can say that the population standard deviation is between $2,767 and $4,816. And that's your answer.